In this, we're going to learn that have three variables. And we are sticking to linear systems right now. The next video will show nonlinear. We're going to use the same exact skills we did in the last video. We're going to use substitution and we're going to use elimination. I'm going to go ahead and warn you, I'm going to use elimination a lot more. That is what I feel is, for me, more comfortable and it is faster. I will show you one example with substitution. And just like I did with the last video, it's going to depend on kind of the equation that's been given to me. If it is a situation I think it is easier to substitute, I'm going to do that. If I think it's a situation easier to eliminate, I'm going to do that. But like I said, 9 times out of 10 on these, I'm going to use elimination. So we're just going to jump right into it. I want to solve the following systems. And so let's start with the equation 2x plus y plus 2z equals 18. X minus y plus 2z is equal to 9. X plus 2y minus z is equal to a 6. And so what we saw with the linear systems of equations is we could have one solution, we could have infinitely many solutions, or we could have no solutions. We're going to see a similar three things arise. I'm going to solve this first one, just solve it right away, and then we'll talk about the possibilities for solutions and how those would arise. So like I said, I'm going to use substitution, not going to use substitution, I'm going to use elimination on a lot of these. I'm going to leave it up to you what you prefer, but I do think elimination tends to be easier. And the other thing I'm going to do, just to make it a little bit easier to reference, is I'm going to name these equations 1, 2, and 3. And that way you guys can see when I'm dragging these things off, which one I'm using a little bit easier. And I'm using Roman numerals just to not get it confused with the numbers, the coefficients. So if I'm going to use elimination, I need to find one of my variables to eliminate. And I'm going to use a lot of the same ideas that we did in the last video, that I'm going to be looking to see if there is an easier variable. So if I look at the x's, I have an x which is a factor rather of the 2 and of the x. So the x's look pretty easy. The y's, well, I have a 1y and I have negative y and 2, so those look pretty easy because again we're looking for those factors and 1 is a factor of both negative 1 and 2. And then z's, I have a negative 1, I have a 2 and a 2. So again, the z's are looking pretty easy to me. Not a lot of difference here. I'm going to actually eliminate the y's. And the reason for that, I'm going to use the second equation to eliminate both the other y's, the first and the third. The reason for that, I'm looking for that 1y because 1y is always easiest to multiply to get to match with other things, or anytime we have those coefficients 1, those are the easiest to multiply by. But the other thing I recognize is that that y already has an opposite sign of the other two. And so for that reason, I think it makes it a little bit easier. When I do my elimination, I don't have to worry about subtracting equations. I can simply add the equations. And to me, that's just a degree easier. The z's wouldn't have been a whole lot harder. It's just the y's already have a 1 and negative 1. So what I'm going to do to start with is I'm going to take the first and second equation. And I'm going to just add those two things together. So we have our 2x plus y plus 2z equals 18, and x minus y plus 2z equals 9. So if I add these, the y's eliminate, leave me 3x plus 4z equals 27. So notice what we did. We started with something with 3 variables. We eliminated a variable the same way we did with 2 variables. And now what I have is a 2-variable equation. So at this point, I'm halfway to where I was in the last video. I'm halfway to having just that 2-variable, 2-equation system. But one equation is not going to be enough. Like what we saw with our last videos, we had to have 2 equations with 2 variables in order to eliminate or in order to substitute. And so what I'm going to do next is I'm going to choose another 2 pairings of equations. I cannot choose the same 2 obviously because I'd get back to the exact same thing, but I want to choose another pairing. So I could choose 1 and 3 or I could choose 2 and 3. And what I said I was going to do, I was going to use 2 to eliminate the other 2 because I like the fact that it already has that negative switched. But the other thing I recognize is that that negative 1 and that 2 are not going to cancel out as it is. I need to multiply the second line by a 2 so we get a negative 2 to cancel with the 2. So I'm going to take 2 and multiply it by that second line. So when I do that, I get a 2x minus 2y plus 4z equals 18. Just multiplied everything by 2. And then I'm going to copy that third line over exactly as it was. So we have an x plus 2y minus z equals 6. And so now that those y's are the same coefficient except for with the opposite signs, I can add them to eliminate 2x plus 2x plus 1x is 3x. The y's cancel. And then we have a 4z minus z, that's going to be a 3z. And 18 plus 6 is 24. So now we have two new equations, and I can, if I wanted to label them, I could. My tablet's being glitchy again today and not switching colors on me. So if I want to call this equation 4 and 5 just to reference them, I can. It might make it easier down the road. But I've created two new equations. These new equations have to be true. The same way when we're doing our just two variables systems, we could always add, subtract two equations and keep a true statement. These have to be true statements. So what I'm going to do now is I'm going to just take these two equations and I'm going to combine them in some way to eliminate another variable. So if I look at them right now, I have the 3x and the 3x, they are already the same. So I'm just going to put those equations one on top of the other. And I'm going to subtract, because if I subtract right now, the x's will eliminate. 4z minus 3z is going to be 1z. 27 minus 24 is 3. And so now I know one of my variables. I know that z is equal to 3. I'm going to do exactly what we did before, which is to start plugging this back into the other equations. Now, I have many different equations here. I have 1, 2, 3, and the fourth and the fifth ones that we created a minute ago. I don't want to plug into those three originals because notice I still have three variables. So if I plug in one variable, I still have two unknowns. I'm going to come back to either equation 4 or 5. I'm going to choose one of those to plug this z in, and it really doesn't make any difference. I'm going to look for the easier one. In this case, I don't think there is an easier one, so I'm going to plug into 5 just because I have a little bit more room under it. So I'm going to plug in my z. I'm going to obviously multiply those, subtract over, and we get x to be equal to 5 when we divide by 3. So now I have my x, I have my z, I still need my y. So now is when I come back around to using one of those initial three equations because they're the ones with all the variables included. So I'm going to choose whichever one I think looks easiest. They all look pretty easy. I'm going to choose maybe the first one because it already has that y. That's just y, doesn't have a coefficient. So I have 2 times my 5 plus y plus 2 times my 3 equals 18. So this would be 10 and 6, that'll be 16. And then subtracting the 16 over, I get a y equals 2. And so we end up with an x of 5, a y of 2, and a z of 3. That is our answer. We have solved it. In the same way we could with two variables, I can take that, I can plug it back into any of my three initial equations. In fact, I need to plug it into all three of my initial equations to check that in fact I have the right point. And we could do that. I'm not going to spend the time in this video, but it's always a good idea to check your work, especially on graded assignments. I kind of launched right into this one. I just said solve. And we see that we're using the same skills as before. We had to eliminate one of the variables first to get it down to that two variable two equation system. And then we did the exact same thing we did yesterday. We just had to remember to find all three variables, not just the two, not yesterday, but in the previous videos. So using the same skills, but we're just kind of adding another layer on top of it. We have to eliminate a variable to get down to that two equation two variable system. We can do this for any number of variables. It's going to work the same way. Obviously, we see that it takes more time. So if we have something with 10 variables, that's going to take a lot longer to get down to where we need to be. That's going to be a lot more tedious of a process. And so at a certain point, we're going to switch over to using matrices. And matrices are going to make this a little bit more efficient, going to allow us to use technology as well. And so that's really what we would do if we came across something with, 4, 5, 6 variables. I wouldn't solve that by hand. I would set it up in a matrix, and we're going to learn how to solve that, like I said, with technology. But for right now, I do want us to be comfortable solving these things by hand, understanding that it doesn't matter if we're adding more variables, we're doing the same processes. Now, we added a third variable, but we also added a third equation, and that's going to have to be true. If we want to have a chance of getting to a dependent solution set, notice this is dependent, we talked about those definitions in the previous video. We have obviously a consistent set of equations, we could solve it, and we got one variable, so it is not dependent, but independent, rather, independent, because we have that one solution. If we want to have a chance at having independent solutions, we have to have the same number of equations as we do variables. If we have more variables than equations, we are guaranteed to have a dependency, a dependent solution set, where we have one of those things we have to solve x in terms of y or z in terms of x. We'll look at those down the road. But we should always kind of be hoping that we have the same number of equations as variables. If we have more variables and equations, we're not going to have a chance at getting to a single solution. We'll have an infinite solution set. All right, let me also talk about how those would look. So if we have this single solution with lines, we said that is the intersection of two lines in the plane. Wherever they intersect, that is the point that solves it. If we had those infinitely many solutions, we saw where we had a line on top of a line. If we had no solutions, we saw those two parallel lines. If we're dealing with three variables, that means we are now dealing with an x-plane, a y-plane, and a z-plane. X, y, and a z. And z we typically think of as a height, or that's a good way at least to visualize it. So, if you're kind of sitting down right now, if you think about the right and left to you as being the x-axis, forward and backward of you as being the y-axis, and then up and down from the floor is your z-axis. And so we have this three-dimensional plane, and so if we're putting a line through it, it's no longer just a line. What we're looking at is a plane within space. A plane, think of holding up a piece of paper in front of you. That is a portion of a plane. Planes are like lines in that they are infinite. They extend all directions infinitely. But they are completely flat. They have no width to them the same way that lines have no width to them. So again, like I said, think about that piece of paper and extending it out every direction infinitely. So I'm not a very good drawer, and I'm not going to try and draw these with a lot of detail, but if we think about each of the cases, the case where we have this independent solution set, what we just saw, when we get that is the intersection of three planes. So if you're in a building right now, think about the walls, the floors, and the ceiling of your room that you're in as planes. If you look at where two of those walls meet, if you look at where they meet, they are forming a line. The corner of the room is a line. So if we only have two planes, try my best to draw this, they are going to meet on this line right here. They're meeting at a line. So that's why I'm saying if we have three variables, if we're working in this three variable space, we're going to have that third equation in order to find a single point. I'm going to draw a third plane, or do my best. There we have our third plane. And now notice where all three of these things meet. We have our right wall, we have our left wall, and then we have our third plane. They're meeting now at a single point. And so if you want to visualize this in your room, think about those two walls that you were just looking at a second ago, but now look at the ceiling as well. Where all three of those meet is at a single point. Now, if we had these three planes, do they always have to be intersecting with one another? No. It could be that those three planes are sitting on top of each other. So think about, or physically take three pieces of paper, put them on top of each other. Those planes, those pieces of paper, intersect at all of their points. That is an infinite solution set, or a dependent solution set, as we called it yesterday. So literally just stacking those three pieces of paper, one on top of the other. But of course they extend infinitely. And then the third case, where we had inconsistent equations. Remember we called these first two consistent. Independent, dependent, those were consistent solutions or consistent equations. They gave us independent or dependent solutions. Inconsistent equations, in the case of lines, never touched. Well, it is completely possible to think about three planes that never touch. They would be sitting one on top of another, but with space in between. So to visualize this, think about your floor and your ceiling. They are, even if you extended them out infinitely, as long as your building is built correctly, they will never touch, right? They will never come any closer to one another. And so it could actually be that one of these planes is intersecting with them, right? I could draw another plane across them. So think about one of the walls and your floor and your ceiling. the wall and the ceiling intersect on a line, the wall and the floor intersect on a line, but the ceiling and the floor never intersect. So where do these three things overlap? They don't. There's never a place. So those are inconsistent. So there's actually multiple ways to get inconsistent equations. Now you could think of 3 stories, those stories never touching, or you could think of just 2 stories and a wall in common, those 2 stories never touch. And so we can end up with those inconsistent equations. With our dependency, there's actually multiple ways to get this. It could be that we have 2 of those planes sitting one on top of another. Again, think about 2 pieces of paper. And then we have a third plane that is actually intersecting them both. Well, they now intersect on that line. So they have an infinite solution set, not across all of the plane space, as in the first example where the pieces of paper are sitting on top of one another, but they have now a line as their solution. So we'll see some examples of how these work as we get through the videos. Before I get too far into the weeds, I want to do an example where I use substitution as well, and I want to show you how it might be set up where I would want to use substitution. Even though I prefer elimination, I still might use substitution in this case. So we have the equations x plus y equals 4, x plus z is equal to 2, and y minus z is equal to 5, and again our instructions are to solve. So right now this is looking much simpler than the last one because we do have 3 variables, but each variable, in each line there are only 2 variables, and that makes it a little bit easier. Because there are only 2 variables, it is maybe a little bit easier to rearrange in this case rather than trying to eliminate. I don't actually, in this one I probably still would eliminate, but this one is a lot easier to do substitution because it is a lot easier to solve for one of the variables. For instance, I could take this first equation, x is equal to 4 minus y, and now right away I've solved for an x variable. So I can plug that into my other equation. So if I plug that into my second equation, I'd have 4 minus y plus z is equal to 2. But notice that hasn't really helped me. I have gone now a y and a z. But it has helped me in a way because I have this equation down here, which I can also solve for either y or z. Let's go ahead and solve this one for y. So y is equal to 5 plus z. And so now that y that I just added in there a second ago, I can go back and replace that as well. So we'd have 4 minus 5 plus z plus the other z equals 2. So we solved here. We plugged that into our second equation. We solved for the y. We plugged that into the y of the other equation as well. And so now we have an equation with only z's. I'm going to do a little simplification. 4 minus 5 minus z plus z equals 2. And notice what is happening to my z's. They're eliminating. I have 4 minus 5, which is negative 1, equals 2. And so what is this telling me? This is telling me that I have an inconsistent solution set because once again we've used substitution, could use elimination, it doesn't matter. We've gotten to a point where we have 2 sides we're stating are equal to each other, but clearly they are not. And so this is impossible. So this is an inconsistent set of equations, meaning we have no solutions. And so there would be an example where we have the possibility of using substitution. We could do that on these more complex ones as well, but think about it. We're going to have to solve for an x, have it in terms of y and z, plug that in. Then we're going to have to do kind of the same thing on the others. It's going to be a lot more work than I think what the elimination is. Not that it's not possible here. Still not, the most immediate thing in the world. It took us a little bit of work, but it really wasn't terrible doing substitution on this one. Elimination, I think, would be just as easy. All right, let's move on to another example. So this one we have 7x plus 3y minus c equals a 13. Then I have x plus 9y plus 2z equals 19. And last, I have a negative 4x minus 5y plus z equals negative 14. Now, just like with our two variable equation systems, we do need to make sure all our x, y's, z's are on one side. We want to have all these variables on one side before we start elimination. So if it's ever not, you have to do a little bit more work, but that should be pretty simple, just kind of rearranging, moving things around. So my numbers are a little bit bigger on this one, but it's going to be the same exact idea. I'm going to use elimination. I'm going to look to see, is there an easier variable? Well, here's a good case where the y's are definitely not the easiest. 3 is a factor of 9. It's not as easy as a factor of as 1, but 3 is not a factor of 5, so I definitely not use the y's. The x's and the z's, I have a slight preference here, but I think you could easily make a case that either of them is not terrible, right? We have the 1x that's easy to cancel with other things, just multiply it by 7 or 4. But then on the z's, we already have that sign switched. The numbers are a little bit smaller, so that just means I have to multiply by a little bit smaller of a number. Here I would have to multiply this one by a 2 to get it to cancel here, and then with the first and third I could just leave them alone. So I'm going to cancel out the z's here. I'm going to label these equations the same way I did in that last example. So let's start by eliminating the z's in the first and the second line. So what that tells me to do is multiply the first line by 2, so that way it will match in the second line. We'll have 14x plus 6y minus 2z is equal to 26. Then we have the x plus 9y plus 2z that I have not changed. That's equal to the 19. I'm going to add those two equations. 14 plus 1 is 15. 6 plus 9 is 15 as well. Negative 2z plus 2z, they cancel. That gives me just a 0. And then 26 and 19, that would be 45. And then I'm going to combine the first and third row. Again, why those two? Because the z's are going to cancel nicely. So this time I was using that first line to cancel off all the others. The first problem I did, I used the second line. So I'm going to do it right underneath. I would lay this out better if I was working on paper that I could show you everything at once. I would kind of move straight down rather than jumping around the screen, but it's hard when I can only see a portion of the screen at a time. So here, I'm going to add these two things together. The z's will cancel. I have a 3x and a negative 2y equals a negative 1. So now I look at these two equations, and I would say I need to get the x's or the y's to match. I'll call this the fourth equation and this one the fifth one, just so I can reference them. What I do notice about this fourth equation is right now the numbers are relatively large. They're all, in fact, a factor of 15, or I should say multiple of 15. We have 15, 15, and 45. We could factor everything by 15. We could do that. That might make the problem a little bit easier. Also notice that 3 does go into 15 5 times. But I think it's going to be a little bit easier just to make these numbers smaller. So I'm going to divide everything by 15. So I'd have x plus y equals 3. So I've just created a new equation. I took this fourth equation and divided it by 15 just to make the numbers a little bit smaller. And so that makes it a little bit easier to cancel these equations out. I could either multiply the x's by 3 to get it to cancel, or I could multiply the y by 2. I'm going to choose to do the y. So I'm going to multiply this thing by 2 in my next step, and I get 2x plus 2y equals 6. I have the 3x minus 2y equals negative 1. So this thing I just created, I'll label it as my sixth equation. I took 2 times the sixth equation right here, and I took the fifth equation. I'm going to add those together. 5x, the y's cancel, equals 5. So our x is equal to 1. Now that I have my x, I can go back and solve for my y would be the next step because I have two equations with an x and y. I don't want to try and solve for z yet. So I'm going to plug it into this sixth equation actually, just because that's the smallest number that I see, the smallest numbers. And subtracting that one over, I get y to be 2. And now I have to go back to one of the 3 initial equations. and I'm trying to solve for z, I think that third equation is going to be the easiest because it has just the z in it, not a 2z or a negative z. So I have negative 4 times 1 minus 5 times the 2 plus z equals a negative 14. Negative 4 minus 10 plus z is equal to negative 14. This is negative 14. When I add that over, I get z to be equal to a 0. And so my solution is 1, the y is 2, and my z was 0. And so there is my solution. It is a consistent set of equations with an independent solution. Let's do one more example. Let's take the equation 2x plus y minus 3z equals 0, 4x plus 2y minus 6z is equal to 0, x minus y plus z is equal to 0. So again, here I have options. I think the x's wouldn't be terrible. The y's also wouldn't be terrible. We have a 1z, so the z's wouldn't be terrible. Because we have coefficients of 1 on all of those. I like the fact that the y already has a different sign. The z does too, in fact. But the numbers are just a little bit smaller, so that means when I go to multiply, the numbers will just be a little bit smaller. So let me take the y's and let's eliminate them once again. I see that the first and third equation would cancel out really easily, so let me start with those. I'm just going to rewrite them. So we have the 2x plus y minus 3z is equal to 0. And we have an x minus y plus z is equal to 0. I'm going to add those. We get 3x, the y's are gone, and we get negative 2z is equal to 0. So there is one equation. Then I will also take the second and third equation, because I like the fact that the signs are already opposite. I just see more mistakes. When you're going to try and subtract, I see more mistakes in forgetting to distribute the negative. So I'm going to leave the second equation as it is. And those y's, I'm going to multiply them by a 2. I want to multiply the y's by 2, which means I need to multiply the entire third equation by 2. And so now I'm going to add these two equations together, get a 6x, a negative 4z equals 0. And so now I've created a fourth and fifth equation here and here. If I look at that fourth and fifth equation, the x I could eliminate by multiplying the first equation by 2. In the z, I could eliminate the z by multiplying the first equation by 2. So it actually requires the same elimination number. Let's see what happens when we do that. I'm going to multiply 2 times the fourth equation, bring down my fifth equation. So we'll have 6x minus 4z equals 0. We'll have another 6x minus 4z equals 0. And I'm going to add these. I'm not going to add, I'm going to subtract because I need them to go away. The x's cancel, the z's cancel. I'm left with the statement 0 is equal to 0. Hopefully remember what this means from our previous video. This does mean that we have infinitely many solutions. This tells us we have a dependent solution set. And so just like we did yesterday or in the last video, we're not going to just stop here and say there's infinitely many solutions. We're going to express all of these solutions in terms of one of the variables. So what I'm going to do is I'm going to go ahead and say, let's let z equal t, where t is just some real number. Same way we did before, that we are just saying, hey, this variable, let's assign it a value. It is a fixed value at this point. It is some number t, and we're going to solve the x and the y off of this t. So we have an equation here with an x and a z. And so I can solve this for the x. The first one looks to be a little bit easier. So I'm going to have 3x minus 2 times, remember we're assigning that z the value of t just so we can fix it, so we don't have this problem that we have a variable in our answer. To solve for x, I would add my 2t over. and then I would divide by the 3. So x is equal to 2t over 3. I also need to know what y is. So I'm going to take one of the equations with y. That first one definitely appears to be the easiest. I'm going to plug in what we found to be the x, and remember that we have assigned z to be equal to t. And so our first equation, we have 2 times the x, 2 times 2t over 3, plus the y, minus 3 times t, equals 0. Let's do a little simplification. So we have 4t over 3 plus y minus 3t. I can simplify those t expressions, but I need to have a common denominator, which would be 3. So if I put a 3 here, I need to multiply the top by 3 as well. So we have a 4t minus 9t, which is a negative 5t. And so then solving that for y, we get y to be equal to 5t over 3. And so now we have the solution. The solution is 2/3 t, 5/3 t, t. And so what we stated in the previous video, that anytime we have that dependency, we still want to write the solution set. We still do want to write that solution set, but we are going to have to do so in terms of an unknown constant. We've assigned one of the variables a constant value. We haven't stated what it is, we're just saying it's some constant value. We've found the other variables too in terms of that constant. So this would be an example where we have those 3 planes overlapping or a pair of planes overlapping. We can find what the solutions are, we just have to do it in terms of an unassigned constant.